Welcome to Atiigah Tech Academy. Today we'll continue with our applied electricity video series. Today we'll be tackling Norton's theorem and we'll solve problems and solutions in Norton's theorem. So, what will this video cover? This tutorial will cover the concept of Norton's theorem and the importance of Norton's theorem. And after doing that, we'll learn how to calculate the Norton's equivalent circuit. That is, how to calculate the Norton's resistance and the Norton's current. And we'll finally solve examples to demonstrate the step-by-step application of this concept we've learned. And please, in this video, you see, we are going to break down Norton's theorem. Norton's theorem is a powerful method for simplifying complex electrical circuits. So, to become just a simple circuit that you can simply use current division rule to now find the current through the resistor. So, this video is perfect for students, anyone learning applied electricity or learning anything related to Norton's theorem, and anyone looking to strengthen their circuit analysis skills. Kindly watch till the end to gain a solid understanding of these essential electrical engineering principles. Please don't forget to like, share, and subscribe for more practical tutorials. And also leave a comment. If you don't understand anything, you need any further clarification, leave a comment. So without wasting much time, let us dive into our Norton's theorem concept. With Norton's theorem says that when a circuit like this is given to you, you see, they've given us this circuit. So he says when a circuit is given to you, we have our resistors here, our voltage sources here, and all the resistors here. He said to find the current. Let's say if we want to find the current across this load resistor RL, he said we should simply remove the resistor from the circuit. So we should remove the resistor from the circuit and replace it with the Norton's current IN. So let's remove the RN. So after removing Rn, we redraw our circuit to this. So we've now replaced we've removed this resistor and we've now replaced it with In. After removing it and replacing it with In, he now says you should calculate the In, this In, using KCL and KVL, either KCL and KVL. So let's say if we want to calculate IN here, we can say this voltage delivers a source. When it gets here, it's placed into 2. So we can apply KCL at this node and write maybe a KVL equation for this and KVL equation for this to solve IN. So going forward, he said after removing the resistor and solving for IN, we need to also come and solve for our RN, that is the Norton's resistance, and the IN is the Norton's current, or we can say the short circuit current. So after calculating these two, we can also calculate the Rn by it's just same as the Thevenin's principle, but here there's a difference. Rn is equals to Rn, because in Thevenin we just also remove the resistor and short circuit voltage sources, open circuit current sources, and in this case it's the same. So to calculate our Rn, the Norton resistance, you realize that R1 and R2 are in parallel, so we simply do that. We calculate our parallel resistor, so we know how to calculate resistors in parallel. So after finding that, we now need to draw the equivalent circuit. So the equivalent circuit for Thevenin is this. This is the equivalent circuit, that is the IN in parallel with the Thevenin resistance in parallel with the RL we removed, the load resistor we just removed. So after doing this, we realize that this Rn and RL are in parallel. So let's say if I want to find the current IL through this resistor, what do I do? If you look at this circuit carefully, it resembles the circuits we use to apply the current division rule. So here you can simply apply your current division rule. So at this end, to apply our current division, we set to find the resistor in this one, we take the opposite resistor. So the opposite is Rn. So our IL is equals to our Rn all over the sum of the two resistors, Rn plus RL, times the total current. The total current here is In. So since then, we can just write our equation as this. So this is how to find the current across any resistor in a circuit using the Norton's principle. So this is the step-by-step approach you need to go through in order to use the Norton's principle. So we'll take some examples to really apply this these concepts we've learned here and see how we use it to solve problems. We should find the current in the 5 ohm resistor using Norton's theorem. All resistances are in ohms. So to apply Thevenin's here, Thevenin says that we should remove the resistor. This is the resistor, so this is our next circuit I've drawn. So we should remove the resistor and replace it with In. So I've removed the resistor and this now becomes In. But let us look at something. At this node, we realize that In is leaving this node, right? But when it gets here, In splits into two. Do you realize it? So let us name this one. Also delivers this source also delivers a current. So let us name that source I2. That current, because the current will be entering, right? I2. And since that is I2, meaning here applying KCL at this node, at node C. Applying KCL at node C, we'll say sum of currents entering is equal to sum of currents leaving. So the currents that will be leaving node C are IN plus I2. And at this node, the current that will be passing through this 2 ohm resistor, because when it gets here it will split. The current that will be passing this through node resistor will be In. In will be passing through it. And when In gets here too, In will also come back here. So let us also name the current passing through this one as I1. But realize that I1 will add up here to come here too. So that will be In plus I1. Hope you get it. And here I1 also flow through the circuit. So I1 is what is flowing through the circuit. This I1, yeah, I1 is flowing through this resistor. Then what do we now do? We now have to take our loops, because we've applied KCL. How I simply wrote this equation is I applied KCL at the various nodes, because when this one gets here, it's split, because it has to come back. It came from here, so it has to come back. So applying KCL in A, B, J, A, H, KVL. So let us move in the clockwise direction. Applying KVL, we know that here is 7 volts, right? So applying KVL, we get in that loop, we get our voltage source, because we are moving from a lower potential to a higher potential, which is 7, times 2 I1 plus 2 In plus 3 I1, because it's all going in the same direction as our flow. Then we add it up to get our equation 1. When we simplify it, we get this. And also taking the second loop, we take our second loop, we take this loop A, D, E, H, A. Taking that loop, we write our loop equation. So we are moving from a lower potential to a higher potential. Voltage source, the sum of voltage sources equals to voltage drop. So it becomes 7. Here we are moving from a lower potential to a higher potential, plus 10. 7 plus 10 is equals to the voltage drop across this 2 ohm resistor. the voltage drop across this 2 ohm resistor and the voltage drop across this 2 ohm resistor. So it now becomes 7 plus 10 is equals to 2I1 plus 2IN minus, because you see, do you understand why it's minus? Because we are going the clockwise direction, and since we are going the clockwise direction and it's against our flow, it's going the opposite direction, that's why we minus it. Minus 2I2 plus 2IN, this 2IN, those are the things we take. Simplifying this equation, we get 17 is equals to 2I1 minus 2I2 plus 4IN. Afterwards, we now take our last loop. This our last loop. We take our last loop. So taking this last loop, we realize that 2 0, because here we don't have any source here, any voltage source here. You see that we don't have any voltage source here. And here we are moving also in the clockwise direction. So we have our 2IN minus, because we are going in the clockwise direction. Here we are taking it like this, in the clockwise direction, minus our 3I1 because it's going against our direction, then plus this 2IN plus 2I2. So simplifying it further, we have 0 here is equals to minus 3I1 plus 4IN plus 2I2. So what do we now do? We realize that this equation 2 and equation 3 are somehow similar. So we simply add those two equations. So we add equation 2 and 3 to get equation 4, which now becomes 17 minus I1 plus 8IN. Then afterwards, we now solve equation 1 and equation 4 simultaneously. So we now solve equation 1, equation 4 simultaneously. Then after solving them, we get our answers as I1 is equals to 11 over 21. IN is equals to, this was what we are looking for, IN is equals to 46 over 21. So after getting our IN, we now come back here. We come back to this circuit. Thevenin says to calculate our RN, the Norton's resistor, we should short circuit voltage sources and open circuit current sources. And how do we do that? Doing that, we've short circuited this voltage source and this voltage source. That's why we now have our new circuit as this. So we calculate our RN here. And what do you realize? You realize that these two and these two and these three are in parallel, in series with this, and these 2 and 2 are in parallel. So we simply calculate them. So we can write them here as finding our Rn. 2 in parallel, you write this. I told you already in our subsequent videos that in parallel just write 2 bars. So 2 and 3 are in parallel. That's why I denoted it as this. In series with 2, and these 2 and 2 are also in parallel. So I simply now apply my mathematics here. 2 times 2 over 2 plus 3 plus 2 plus 2 times 2 over 2 plus 2. Then I get my Rn as 4.2 ohms. After getting my Rn and my In, I now draw my Norton's equivalent circuit. Drawing my Norton's equivalent circuit, this is what I get. They said I should now put the resistor I removed back. So the resistor I removed was 5 ohms. So I now have my In here. So our I. So now how do we calculate for our I? So our I here is now equals to, we know our Rn. Rn is 4.2 and here is 46 over 21. So now using current division rule, I can use current division rule to find the In. I know the total current, I know this resistance, and I know this. So I take the opposite resistor, which is 4.2. So our 4.2 all over the sum of the resistors, 4.2 plus 5 multiplied by our 46 all over 21. So after doing that, you end up getting your answer as 1 amp. So the current through this through this 5 ohm resistor. It was 1 amp flowing through it. And in our next video, what I will do is that I'll use simulation to really prove to you that it's 5 amp flowing through this current. So I'll use a simulation to show you in our next video. So let's take our next question. So if you don't understand anything, you can just pause, look at how the current distributions go. Your current, making, depending on how you assign your current, can make your circuit, your question complex or not. So always figure out a way you can simply assign your currents and you'll be good to go. So moving to our next question. Using the Norton's theorem, find the current in the 0.1 ohm resistor. All resistances are in ohm, and we know that 100 milli is simply 100 times 10 raised to the power minus 3. So you can just do the conversion. So after doing the conversion, we realize that looking at this circuit, they said we should, Thevenin says the resistor that you are find the current, you Norton's, you remove it across it and name it IN. So we name it IN, but let us now apply KCL and KVL at the various nodes. Let us apply KCL at this node. Applying KCL at node B, we realize that this current is leaving, right? IN is leaving node B, and this 5 amp is entering node B. So that means 5, there will also be a split here, so current will also leave here. So the 5 amp, to get the current flowing here, this one is also entering. It says KCL says sum of currents entering is equals to sum of currents leaving. So here, since we know the current is 5 amps, so it becomes 5 minus IN, because those entering is to get the current leaving here. Those entering is equals to those leaving. And the total current that was coming is 5. So doing our mathematics, that is what we get. Then we also come here, we do the same thing for this side. We know that 2 amps is entering and IN is also entering. So what will be the current leaving? So the current leaving will be the sum of this IN and the 2 amp. So here we get, because here is entering and here it now leaves, so it will become 2 plus IN. That will be the current leaving here. So here we simply apply KVL in this loop. So applying KVL in that loop, I even wrote it here, applying KCL at node B. At node B, you realize that the 5 is equals to 5 minus IN. Then applying KCL at node B, just as I explained, we realize that that is what we get. And now applying KVL to loop BCFGB, we now apply it here. So we don't have any voltage source here, so they are all voltage drops, so it's equals to 0. So we have this, our 0.5 times this, the whole of this, then plus our 0.4 times the whole of this is equals to 0. So doing that, we get this equation, and this equation we now expand it, and it simplifies to give us this 0.9 plus this. So we can further simplify to find IN. Finding IN gives us 17/9. So here we see that you could simply found IN easily. Now to come and find our RN, the Thevenin resistor, he says we should open circuit all current sources and short circuit voltage sources. Let us look. This is a current source, this is a current source. That's why I open circuited them. You see they are open circuit here, open circuit here. And here we now need to calculate our RN. To calculate our RN, realize that our 0.5 and our 0.4 are in series. This resistor and this resistor in series. So we simply find our RN by adding them up. So 0.5 plus 0.4 gives us 0.9. And after finding, we now know our RN and our IN. We simply now calculate our Thevenin We draw our Thevenin equivalent circuit, and drawing our Thevenin equivalent circuit, this is what we get. Then we draw our resistor, we remove back. So after drawing our resistor, we move back, which is 0.1. We now find the current through that resistor. Apply. We know here we got 17 over 9, and here was 0.9. Rn was 0.9. To now calculate our current through the one, let's name the current I. So the current through the 1 ohm resistor is equals to the opposite resistor, that is 0.9. Our 0.9 all over our 0.1 plus 0.9 times 17 over 9, which is now equals to our 1.7 amps. So the current through this resistor is 1.7 amp. So that is how we calculate using Norton's theorem. That is how we use Norton's theorem to calculate a current through a particular resistor. So we'll take our second question, and I hope you guys are really getting it. Using the Norton's theorem, find the current in the 10 ohm resistor. All resistances are in ohms as usual. So they said we should use the Norton's theorem as we've always been calculating. This is the 10 ohm resistor. Here is 10. So that's the 10 ohm resistor that we are calculating. So what we do is that we've removed this is our question. We have to remove the 10 ohm resistor from the circuit as usual. Then we will now remove it and replace it with our short circuit current, IN. What do we realize? We realize that this voltage source will deliver current, right? It will deliver current. So let us name the current that will pass through this circuit as I1. And we also realize that there's also a voltage source in this loop. This voltage source here will also deliver current, right? Because even if this current gets here, it's placed into 2. So let us name it as I2. So we now have to apply KVL and KCL in order to find this question here, to find the things here. So here we can apply KVL to this loop. So applying KVL to this loop, finding I1, to find I1. So let us try to find I1 first. To find I1, we know that this is our voltage source, and here the current we have to, cause I1 flows through only this resistor, and since I1 is flowing through this resistor, we can simply calculate the current by dividing the current through it, this I1, by dividing this voltage by the resistance. So it writes as 10 is equals to 4I1, then I1 is equals to 10 over 4. That is how to calculate the I1. Moving forward, we now have to also apply KVL to loop A, B, E, D, A. So we now apply KVL to this whole loop. So applying, and we'll take the clockwise direction. Taking the clockwise direction, realize that we are moving from a lower potential here to a higher potential. That becomes, let's look at the voltage. This becomes 10 here, positive 10, and we are coming here, we move from a higher potential to a lower potential. This becomes negative, so it becomes 10 minus 12 is equals to our 4I1 plus our 6I2, but we know the value of I1 already, so here is 12, it's not 2, it's 12, it's 12, it's not 2. So We know the value of that already. After doing our subtraction, this is what we get. We get our answer as minus 2. We get our I2 doing, because we know the value of I1. So we just substitute it back into the equation to simplify the whole thing. Then we come and get our answer as minus 2 amps. It's always good. Don't forget the units. Minus 2 amps. After getting our minus 2 amps, we apply KCL at node B. So after applying KCL at node B, we realize that currents entering, sum of currents entering is equals to sum of currents leaving. So I1 plus I2 is equals to IN. So I1 here is equals to I2 plus IN. Then IN here will now become 4.5 amps, because doing simple change of subjections, we know the values. Then we now come back here to now find our RN, Norton's resistance. So our Norton resistance here, let me write it here, RN. He said we should short circuit all voltage sources and open circuit all current sources. So after short circuiting voltage sources and open circuiting current sources, this is what we get. This is the circuit we get. Realize that this 4 and this 6 are in parallel. So we find it. We just 4 and 6, that is 4 times 6 plus 4, all over 4 plus 6. Then we get our answer as 2.4 ohms. Now we've now found our RIN and our Rn. What do we do next? We simply find our total. We draw our Thevenin Norton's equivalent circuit and calculate the current. So this is our Norton's equivalent circuit. I bring our 10 ohm here, and this is the current through it. So here was 2.4 and here was 4.5 amps. Then we realize that we have to use current division here to just simply calculate our I. So it's equals to our 2.4 all over our 2.4 plus our 10 multiplied by 4.5 amps. Then we get our final answer as 0.8709 amps. So this is how we use our Norton's theorem to solve problems, complex problems. So complex problems now becomes very simple problems that you can simply use Thevenin to now simply solve them. So let us take our last example, and our last example is so simple. So for this last example, I want to pause the video yourself, try your hands before continuing, and leave your answer in the comment section. Leave your answer in the comment section. I hope you have your answers ready. Okay, so let us solve it together now. So they say we should find the current in the 4 ohm resistor using Norton's theorem. So Norton's theorem says we should remove it and replace it with the Norton's current, short circuit current. So after removing it, I'm now replacing it with IN. So I've now replaced it with IN. But what do we realize here? Realize that there is a voltage source here, so it will deliver a current. So let us name the current that this voltage source will deliver I1. Then we realize that when that current I1 gets to this node, when I1 gets to this node, it will there will be a split. So since there will be a split, let us name the split here as, we are applying KCL at node A, so we can find the split as I1 plus IN, because sum of current leaving is equals to sum of current entering. So that will become I1 plus IN. So we now have to apply KVL in this loop and also to find the equations. So for applying KVL in loop FA, So applying KVL in loop F A D E F, that this first loop, realize that our voltage source is from a lower potential to a higher potential, that is 15, is equals to our 10I1 plus our 5I1 plus 5IN. Then we get this equation. Then we simply simplify it down to get 15 is equals to 15I1 plus 5IN. Then we also take our next loop. We take loop A, B, C, D, A. And taking that loop, let us take our loop in the anti-clockwise direction. Taking it in the anti-clockwise direction, that means here we are moving from a lower potential here, our voltage source here, so anti-clockwise, so higher potential to lower potential, that is 6 volt here. Higher potential to lower potential, that's minus 6 volt. So minus 6 volt is equals to here is also moving in the negative direction because we are moving against the flow. Is equals to 5 times IN plus I1. So this is our answer. We get to simplify it down to get this. So 6 is equals to 5I1 plus 5IN. Then we now solve equation 1 and equation 2 simultaneously to find IN. So we get I1 as this, IN as 0.3 amps. After getting that, we now have to come and find Rn. This is our Rn here. And Thevenin said we should short circuit all voltage sources. That's why we remove this voltage source and this voltage source. So we should replace them with a short circuit. What do we realize? We realize that the 10 and the 10 ohm resistor, 5 ohm resistor, they are all in parallel. So we combine them. 10 times 5 all over 5 plus 10. Then this, we get our answer as 10 over 3 ohms. After getting our answer as 10 over 3 ohms, we draw our Thevenin's equivalent circuit. After drawing our Thevenin's equivalent circuit, we will write our 4 ohm here. Here we had 10 over 3, and here was 0.3. To calculate our I, the current through the 4 ohm, I4 ohm is equals to our Thevenin's our Norton's resistance 10 over 3 all over 10 over 3 plus our 4 times 0.3. So we end up getting our I in the 4 ohm as 0.1364 amps. So this is how we calculate resistors in series using Norton's theorem to calculate our current passing through a particular resistor. So basically, see that you take a complex circuit, you simplify it down to become a simple circuit that you can simply use current division to solve. So that is how the Thevenin. This is how we solve questions on Thevenins and other circuits. So with our next video, I'll be doing a simulations to teach you how the currents, to really confirm this our answers, to prove to you that yeah, we did the right thing, we applied our principle right to really arrive at the answer. So have a nice day, stay tuned, take good care of yourself, learn hard. All the best. Thank you. And please don't forget, thank you very much for watching. Don't forget to like, subscribe and share this to your colleagues, because if this video is helpful, leave a comment. And please, you can reach us. This video was taught by Atiigah. You can reach us on these numbers and our email. This is our email address, so kindly reach us on this. Thank you very much.